All right, guys, welcome to the review guide for this situation. I'm gonna try to fix this camera really quick. Let me just see if I can make it a little bit better. Hold up. All right, hopefully things are better now. Anyways, we're starting off. This starts on page number 21 here. I would immediately cross out letter C and D. You don't really got to worry about this for problem number one. And furthermore, I'm also not going to be doing problem number one. If you'd like to do problem number one with me later, you can. It is a wonderful question for thinking, but it is not the one of focus for the review packet. So instead, I'm going to go ahead and go to the next page here, problem number two. I'm going to go ahead and really focus on this question because, you never know when it's going to be really important to know this entire question, for the quiz. So let's think about this guy. The function g of r is pi r squared determines the area of a circle given its radius. Hopefully we know that. If we don't, well, now you do. You are using an 8.5 by 11-inch piece of paper to draw a circle. The circle must fit on this piece of paper. Let r be the radius of the circle that can be drawn on this paper in inches. So I'm going to draw a little picture of this first. There's my piece of paper. That is 8.5 on the top and 11 over here in inches. And we have to draw a perfect circle on the inside of it. And that is a perfect circle if you didn't know. No egg shape, nothing. You tell me it's not a perfect circle and you lose points. Great. So here we are. There's our radius of our circle. One thing that's really important to notice is if I doubled the radius, I would get the entire length of the top of the piece of paper, and that's going to come into play later. However, the circle could have been smaller. I could have drawn it over here, There's a little tiny R out here. Not a big deal if I really wanted to. Let's check this out. Complete the table of values. It says round to the nearest hundredth. Forget that. We're going to go ahead and say leave in terms of pi. What that means is I need to make sure that I am plugging in my value and then not multiplying out using my calculator, because I'm not going to have a calculator on this next quiz coming up here. So leave in terms of pi. So let's check it out. G of 0, plugging 0 into this thing, is going to be pi multiplied by 0 squared, which is of course just 0. Easy. G of 1 is going to be the same thing as pi multiplied by 1 squared. And that's going to be simply pi by itself, or 1 pi. I'm going to put 1 pi. Likewise, g of 2 is going to be equal to pi multiplied by 2 squared, and that's going to be 4 pi. 4 pi. By analogy, I don't feel like doing any more of this. This is going to be 3.5 quantity squared multiplied by pi. And likewise, this last value down here is left here on purpose. Totally blank. You got to figure out what the biggest possible radius is. Well, the biggest possible radius must be half of this 8.5 value. So half of that 8.5 value is going to be 4.25. So the maximum area of this circle is 4.25 squared multiplied by pi. Explain how the two quantities covary. Well, in this situation, it's quite simple. As the radius increases, the area increases. If you wanted to be more specific, you could. You could say as the radius increases, the area increases, and it increases more each time because you're going 0 to 1, and then 1 to 4, and then 3 squared is going to be 9, so it increases even more next time, and then it increases even more the time after that. So it increases more and more and more and more each time. What is the practical domain and range of the function? So the practical domain of this function is 0 must be less than or equal to r, which must be less than or equal to 4.25. It is not possible to have a circle that has a negative radius, and it's not possible to go over 4.25 because of the length of the piece of paper up here. Likewise, the range must be between 0 is less than or equal to the area of this circle. And you could put g of r here instead if you wanted to, or you could put the y value, or whatever makes you happy. Less than or equal to whatever 4.25 quantity squared multiplied by pi is. So you don't have to multiply any of this out. Just leave it like that. Whatever that number is, you could plug it into the calculator if you needed to. Determine a formula for the inverse function g. What kind is the input? What kind is the output? This is a very important question. You need to be able to do the inverses. In fact, the inverse of square functions is all that we've been doing the last couple of days. That's the reason why this question is on this review packet. The undoing of a square is a square root. So we're going to have a square root of some way. There are two ways to think about this. I personally think that the easiest way to do this is to first ask ourselves the question, what is g doing in this function? What is g doing to r? Well, you're going to take, first you're going to square r, and after you square it, you're going to multiply by pi. So if you wanted to undo it, the undoing g inverse of the area, because you're plugging in the area and getting out the radius. This is the radius, by the way. This is the area. If you're doing that, you're going to first divide by pi. And then after dividing by pi, you're going backwards. You're going to, instead of squaring it, you're going to square root it. Boom. Easy enough. That is to say, our input is the area. Our output is the radius done by the square root of a over pi. If that didn't make a lot of sense to you, instead what you could do is simply solve for the other variable. If a equals pi times r squared, because that's what it is, area is pi r squared, solving for r, the inverse function, first things first, you have to divide both sides by pi. And then take the square root of both sides. That's going to work out nice and neat. Please note, you really should have put the plus or minus sign if you were doing it this way, or even really this way, but you can't have negative radiuses, so the minus sign doesn't really matter. Either way, make sure that you're noting that your input is the area and your output is the radius. Sketch a graph of the function g inverse. Here's going to be our square root. Be sure to include accurate points on the graph and label the axes with appropriate quantities. We're just graphing these coordinates, but backwards. We're graphing the x values here and the y values here. So I really would just put like a 1 pi here, maybe further out to 2 pi, 3 pi. Here's my 4 pi, and I got there are my input values, and my radius values are going to be 1, 2, 3, 4.25, and we're starting off at 0. We're increasing slowly up to 1, and all of our square root functions kind of just increase kind of slowly like so, and it's going to keep on going all the way over here until you get to this top value. I just don't feel like graphing the entire thing nice and neat and beautiful, but this is good enough. All right, describe how the two quantities covary. It's the same exact thing. As area increases, I don't know why I capitalized that, the radius increases. Again, if you wanted to be more specific, you could add on to this. You could say something like, as the radius increases, as the area increases, the radius is increasing, but it increases less and less and less and less and less. That is to say, the average rate of change, the average slope, is getting smaller and smaller and smaller as time goes on. You might want to note that. You don't really have to for full credit. Let's go on to the next page. State the domain and range of each of the following functions. So personally, I think it's actually easier just to graph these first, or to have some version of a value first. Every single one of these functions is going to have what I call an anchor point. So an anchor point is simply going to be very, very similar to the starting point of a parabola. It's almost just like a vertex, because remember, these square roots are inverses of these. So what am I talking about? I'm just going to do a little tiny example down here. The parabola looks like this. The inverse of the parabola is going to look like this. Unfortunately, I'm not able to have this as a function because I would fail the vertical line test. I could not input an x value and get two different y values out. So this bottom half is not possible. We only look at this top half. This original value down here is going to be calling my anchor point. I'm going to call it. The anchor point of this first one is going to be 0, 7. It's always whatever makes the inside 0, comma, whatever this value is right here. That's kind of like my vertex, just like my parabola formula. Likewise, for the cube root function, The cube root function is going to end up looking like a nice little S shape here. Boom. Looks nice and cool like so. Please note it has an infinite slope right here. It actually gets vertical right there. Don't need to really know that, but I think it's a cool idea. Anchor point here, -3, -2. Anchor point for this one, 7, 0. Anchor point for this one, -3, -4. Anchor point for this guy, 5, 10. Again, it is the value that makes the inside 0. So in this case, 5 minus x equaling 0 if you needed to solve it. 4 minus x here equaling 0 is going to be 4, +1. All these anchor points. You know what? I'm just going to go through the whole packet and put the anchor point, because I need these for every single question, no matter what it is. So we're just going to do it real fast here. We got 0, 4. We need this next one. We got -3, -2. What makes the inside 0, that value? What makes the inside 0, this value out here? Easy enough. I'm just going to do all of them, like I said. Every single one. Just doing those anchor points nice and fast. Really should start getting good at these. -1, 7. 0, 4. Maybe pause the video and try to do all the rest of them on your own. Might be a good move. 0, 0. Anchor point. Anchor point 0, -6. Anchor point 3, 0. Again, the inside equals 0, the outside value. 1, +5. Anchor point, anchor point, anchor point. Ooh, this one's a little bit tougher. We actually have to solve something. 8 minus 4x is equal to 0. If you solve that equation, add 4x to both sides, divide both sides by 4. Anchor point is 2, -3. Think about that one again. Anchor point, what makes the inside 0? 1, +3. What makes the inside 0? 2, -1. Easy enough. Anchor point, anchor point, anchor point. Okay, going back here. Domain and range. Domain and range. First of all, for the cubic functions, these are free points, all real numbers every single time. ARN, all real numbers. You could also write this as -infinity to infinity, or you could write this as x as an element of the reals, or you could actually just write all real numbers. I don't care. Same exact thing for the range. Pick one of these three. I don't care which. -infinity to infinity, or y is an element of the real numbers, or b of x is an element of the real numbers. I really don't care. Either way, it is what possible values you're going to be getting out for your y values, your range. For cube roots, it's always anything you want. Because this S shape is going to have every single value left and right, I can plug in whatever I want, and no matter what y value I ask it for, it could get to. Please note, some y values are extraordinarily difficult to get to. In order to get a cube root that ends up being 1,000,000, for instance, you actually have to plug in 1,000,000 times 1,000,000 times 1,000,000. That's a huge number. So it's usually not feasible in a real-world situation, but it is still there. Domain and range of these guys is a little bit different, because the square root function typically has this value right here as either the minimum value or the maximum value for x or y. So in other words, we're going to have one of two choices for every problem here. It's either going to be x greater than or equals 0 or x less than or equals 0. It's going to be y greater than or equals 7 or y less than or equal to 7. And again, if you don't want to use y, you want to use a of x, that's fine. It's the same exact thing. We need to pick which one is correct. You can either visualize it, and my favorite way of visualizing it is just remembering a nice, neat little chart. The nice, neat little chart that I'm talking about here is that if you have a positive and a positive on the inside for x, we're going to have that basic square root function. And I did this for my class, putting this entire thing together. We could also have a negative of a positive rad x. And what is happening here? Well, for a positive and positive, it goes up and it goes up and to the right. For this one, it goes down and you have a positive x. It goes down and to the right. If you have a negative on the outside, but a positive on the inside, well, that's what I just did. Shoot. How about a positive on the outside and a negative on the inside? Now it's still going to go up, but instead it's going to go off to the left. Likewise, if I had a negative for both of them, it's going to go down and off to the left. Makes a nice neat little circle. So this guy has a negative on the inside, a positive on the outside. So a negative on the inside, a positive on the outside is this guy right here. So it's going to the left, but it's going up. So it's going to the left, and it's going up. So these guys are not correct. Let's continue on with that same thought process here. The domain here. In this case, we have the 7, 0. It's going to be x is greater than or equal to 7 because I have a positive x. That means x is going to be increasing off to the right. The range here, the range, because that's a negative number, it's going to be everything below this guy. Y is less than or equal to 0. Or c of x is less than or equal to 0. Continuing on here, I have a positive and a positive. That means the x value has to be greater than or equal to -3. The range d of x must be greater than or equal to -4. This guy, negative x, positive. Oh, it's a cube root. Cube root's a freebie. All real numbers. All real numbers. Easy peasy. Square root again. Okay, square root. We have this 4 value, but x is less than or equal to 4 because x has a negative that's going to the left. Look at that arrow pointing to the left. Easy, easy, easy. After this, range, we have a positive number in front. Positive number means this guy goes up. If it goes up, we have f of x. That y value has to be greater than or equal to 0. Easy enough. Same exact concept here, but what I'm saying is you don't have to do domain and range first. You could instead do domain and range last and graph it first. How can I graph these? What you want to do, in my opinion, the easiest way is to create a table of values. The table of values should always make the x value equal to such that the inside of a square root is equal to a perfect square. So in this question, I'm going to set x equal to all of my perfect squares. There's not really much to solve here because x is by itself. So x equals 0, x equals 1, x equals 4, x equals 9. That's good enough for me. 4 coordinates, totally fine. So we got 0, and if we plug 0 in, I'll let you guys do the work out here, but if I plug 0 into this guy, I'll end up getting 4. If I plug 1 into this guy, I'll end up getting 3. If I plug 4 into this guy, again, I'm plugging in these numbers, these perfect squares. I'll end up getting 2. And again, if you want to do that, it's because the square root of 4 is 2. Negative 2 plus 4 is 2. Okay. 9 ends up giving me 1. We just got to graph this guy best that we can. So you got 0, 4. So that's 1, 2, 3, 4 right there. We got 1, 3. That's right there. We got 4, 2. 1, 2, 3, 4, 2. And then I think my hair just got in the way. I apologize about that. And then we got 9, 1, 2, 3, 4, 5, 6, 7, 8, 9, 1. Easy enough. Now what I'm talking about with this domain and range is it's really easy once you have the graph. Because if you look, this original value, the x values all go to the right. So it must be x is greater than or equal to 0, that original x value, that anchor point value. The range out here, the y value goes down. Because the y value goes down, we have that original value, a of x, that y value has to be less than or equal to the original value 4. It starts at 4 and it goes down. The cube root. Similar concept, except this time we need to set things equal to perfect cubes. And now we actually have a more interesting question anyways. Oh, I put that in the wrong spot. Whatever. X plus 3 has to be equal to perfect cubes this time. I think 4 points is easy. X plus 3 equals 1. X plus 3 equals -1. X plus 3 equals 8. X plus 3 equals -8. You want that inside to be a perfect cube. That way you can take the cube root and actually graph this thing. So the table of values that you're going to want to get here. The table of values is going to be subtracting, we already have this original coordinate, sorry, -3, 2, negative. And just graph this up. So putting it in right away, subtracting 3 over here, we're going to get -2. Subtracting 3 over here, we'll get -4. Subtracting 3 over here, we're going to get 5. Subtracting 3 over here, we're going to get -11. Again, I will let you do the work on your own to figure out these guys. You're just taking this and you're plugging it in. Taking this, plugging it in. Taking that number, plugging it in. Taking -11, plugging it in. I'll show you one in the event that you really need to see this. b of -11 is going to be the cube root of -11 plus 3 minus 2. That is the cube root of negative 8 minus 2. That is negative 2 minus 2. The cube root of negative 8 is negative 2, and that's going to give you negative 4. Again, I really do think you should try these on your own. It's not really that bad at all. I'm just going to go ahead and write these answers up really quick. Okay. So now we're going to graph a couple of these coordinates. Again, we're hoping to get this S shape in the end out here. So negative 3, negative 2, that anchor point. 1, 2, 3, 1, 2. That is the center of my S. So my S needs to go whoosh, whoosh, from here. So we got negative 3, negative 2. Then we got negative 2, negative 1. We got negative 4, negative 3. And then you got 5, 0. 1, 2, 3. 1, 2, 3, 4, 5. And we get negative 11, negative 4. That's all the way out here, out there. And again, we get this nice little S shape. Boom. Easy enough. I'm just going to do one more of these because I don't need to do every single one of these questions. You guys can pick how many you guys want to do. I did say pick at least 3, optional but great practice. Do as many as you want. I am going to just continue on to this page and just keep doing this because it's on that same page and I think it's nice and neat to see. I didn't even finish my domain and range here, but it's cubed, so it's easy. All real numbers, all real numbers. Done. So, again, plugging these values in, we have an x, comma, y table, or x, comma, y table. We start off with this coordinate 2, 3, and then we need to set these guys here on the inside for a square root function equal to a perfect square. So 2 minus x equals 1, 2 minus x equals 4, 2 minus x equals 9, 2 minus x equals 16. If you solve these equations, what you're going to get is 2 over here, negative 1, make it a positive 1. This is a 1 here. The next value, subtract 2 over, get 7. You end up getting negative 7 as your correct answer, I think. Oh, I skipped 4, didn't I? Oops. How about, what's that? 2, negative 2, and then negative 7. If you notice, there's a cool little trick here. It goes down by 1, goes down by 3, goes down by 5. Try to think about why that's true. Maybe you can go back to what you were doing in the parabolas problems. Anyways, one more of these. If you solve this guy, subtracting 2 over gives you 14. And you're getting negative 14 overall. As for the y values, if you want to do the y values, again, all you're doing is plugging in this value and seeing what you get. I'm just going to go ahead and do this for you. Please make sure that you are actually trying this out on your own, on occasion. I think it is pretty dang important to be doing. So you plug in 1 here, and you're going to end up getting 2. If you plug in negative 2 here, you're going to end up getting, let's see, 2, negative 2 is 4, negative of 2, so you get 1. And then, yeah, I think you're just going to get 0 and negative 1 here. So we got 2, 3, that anchor point 2, 1, 2, 3, 1, 2, 1, 2, negative 2, 1, negative 7, 0, 1, 2, 3, 4, 5, 6, 7, and then negative 14, negative 1. I don't really have enough room for that, so I'm just going to go ahead and do that. There you go, nice and neat. Notice how this guy lines up exactly with a negative of a negative. It has a swoop off to the left here. Be very careful when you graph these that you're not going to go back up by mistake. You don't want to do that. You don't want to go back up, and you don't want to like randomly go down either. It is a smooth, simple decrease every time. To finish this review packet off, I'm going to do these last couple of questions here, the 7, 8, and 9. Let's check them out. Let f of x be that square root function. Determine a new function, the result of horizontally shifting f 6 units to the right and 2 units down. That means f of x here, or f of g of x must be the same thing as taking that f of x function and shifting it 6 units to the right, that is minus 6 on the inside, and 2 units down, minus 2 on the outside. Let g of x be this cube root function as well, and h of x is the result of reflecting g across the x-axis and shifting the graph of g up 2 units. So reflecting g across the x-axis instead is going to be, so h of x is going to be reflecting across the x-axis is flipping it this way. So you're taking all the positive y values and making them negative y values. So you're going to go ahead and get negative the cube root of x, and it's then up 2 units, so plus 2. Describe how f and g are related. This is called a vertical stretch by a factor of 2. Or g, well, there's not even a letter here. G of x is a vertical stretch of a factor of 2 of f of x. Now, this is really the end of the review packet, but if you want to see another way of graphing these, I'm going to go ahead and graph these using the original concept from the previous chapters that I don't think it really we expanded on enough back in chapter 2, but let's just go ahead and see one more, just so you can see another way of doing these questions in the event that whatever I'm talking about is just not jiving with you, So I'm going to go to letter O here, and I'm going to go ahead and make the original square root value tables right here. I'm going to call f of x the original square root value function, and I'm going to use that as my table of values. And if this makes more sense to you, you can do this for every single question. It's just a little bit harder to do with problems like this letter P where you have the extra negative in front. Come talk to me if you really want. If this method made sense to you, I want you to try it on your own. That way you can see some stuff happening. Try it on your own, but come see me if you want to do it. If you like this way. So I'm going to make the original f of x values, x, f of x, and the original square root values should be very, very easy to have memorized. 0, 0, 1, 1, 4, 2, the square root of 4 is 2, the square root of 9 is 3, and the square root of 16 is 4. They're my original values. Now, this function, what is happening? I'm going to be moving to the right 1 unit. The inputs are moving to the right 1 unit. And then the outputs are getting multiplied by negative and having 5 added. So if I wanted to graph c of x here, or create the coordinates for c of x, instead of doing what I was doing earlier, where you're like figuring out what those values are, setting them equal to perfect squares, setting them equal to perfect cubes, whatever it is in the situation, you could just take all of the values that you've already written down for these perfect squares and simply subtract 1. Sorry, not subtract 1, add 1. I apologize. We're going the opposite direction. So you want to add 1 instead. So I could write 1, 2, 5, 10, and 17. And then the values out here, you get to multiply by a negative and add 5. So you get 5. Multiply by a negative and add 5. Multiply by a negative and add 5. Multiply by a negative and add 5. Did I do this right? Multiply by a negative, add 5. Multiply by a negative, add 5. Multiply by a negative, add 5. Positive 3, shoot. Multiply by a negative, add 5. Multiply by a negative, add 5. And here's your table of values that you could end up graphing. So you get that same exact anchor point, 1, 5, 1, 1, 2, 3, 4, 5. And then you had 2, 4. You got 1, 2, 3, 4, 5, 3. You got all the way to 10 out here, 2, and that should be enough for us. Again, creating this nice little U shape. Again, it really should be more smooth there, but what are you going to do? Domain, same exact idea. X is increasing here, so X is going to be greater than or equal 1. And C of X, Y is decreasing, so it's going to be less than or equal to 5. Hopefully, that is good enough for you guys. You kind of try out which way makes sense to you. I have no idea what they want for the shape of the curve thing, but maybe it's just like, I don't know, maybe it's this thing that I was talking about earlier with my little chart that I had made up. Pick your favorite method. Good luck. If you think I should be re-explaining any part of this, that it was one part was better than another, please ask. But other than that, good luck, and hopefully we do well on Wednesday.